Hello everyone. In this video, I'm going to present the work titled Exploring Filterbank Learning for Keyword Spotting, which was done by me, Ivan Lopez-Espejo, Chonghua Dan, and Jesper Jensen Alvarez from Aalborg University in Denmark. These are the contents of this presentation. So as an introduction, I will talk about the motivation to address this and the objective of this work. Then I will present the two Filterbank learning approaches studied for keyword spotting. And next, I will talk about our experimental framework and experimental results before concluding this presentation. Handcrafted speech features are not necessarily optimal for any particular speech processing task. So, for instance, the famous null-frequency capsule coefficients that are widely used for different speech processing tasks like speech recognition, speech verification, and of course, for keyword spotting, which is the task addressed in this work. So we find that a very recent trend is the development of end-to-end deep learning systems where the feature extraction process is optimal according to the task and training criterion. And within this recent trend, we can find a particular approach consisting of learning an optimal filter bank. And actually, for some applications, optimal filter bank learning has shown improvements with respect to using a standard mail filter bank. So, for instance, for speaker verification, anti-spoofing, or audio source separation and audio scene classification. So based on this motivation, the objective of this work is to explore the possible advantages of employing learned filter banks over handcrafted speech features for the task of keyword spotting. So here we can see a general diagram of a modern keyword spotting system. So the speech signal is first processed by the front end. The goal of it is to extract speech features that are further processed by an acoustic model, normally based on deep neural networks. And in particular, in this work, we will use a deep procedural neural network. Then this acoustic model is responsible for generating a posterior distribution on the different words that the system can recognize. And finally, these posteriors are further processed to make a decision about whether a keyword is present or not. So in this work, we focus on the front-end parts by studying two different approaches. First, Filterbank matrix weight learning in the power spectrum domain. And second, parameter learning of a stochastically motivated camera chip filter bank. And for both approaches, the learnable filter bank parameters are optimized by backpropagation jointly with the keyword spotting backend. So here we can see a diagram of a front end including our filter bank matrix learning approach. And well, first the speech signal is processed to extract from it or to compute from it its spectral representation by means of a STFT, and then the power spectrum is computed by application of a square magnitude operator. And then this power spectrum is the input to the filter bank layer, which applies this linear operation in which W is the learnable filter bank matrix and H is a function, is the element-wise applied ReLU function to ensure the positivity of the filter bank weights. The resulting power spectrum is then compressed by the logarithm operator, and then the result is normalized by means of a batch normalization layer, and in turn, the result is passed to the keyword spotting backend. And this second approach, we consider a stochastically motivated camera chip filter bank with learnable parameters. And we can say here the expression for the camera chip filter bank that is can be considered as the well-known chemical filter bank with an additional term, the so-called chip term, which is a frequency modulation term that yields an asymmetric amplitude spectrum. And the chip term is coherent with physiological observations on frequency modulations and mechanical responses of the basilar membrane. So the speech signal is processed first by the camera chip filter bank layer, and this one applies convolution on the input speech signal by considering a set of impulse responses characterized on this filter bank. And the trainable parameters in this case are the filter gains, A sub k, A and B, which define the envelope of the gamma function, C, the chip term, the center frequencies of the filters, F sub k, and the equivalent rectangular bandwidths. So to preserve the physical meaning of these parameters, the ReL function is applied to the filter gains A sub k, B, the center frequencies F sub k, and the equivalent rectangular bandwidths, whereas n is constrained to be greater than 1. So once we obtain the signals from the gamma chip Filterbank layer, these are to compute the cochleogram, which is further compressed by means of a logarithm operator, and then the result is again normalized by a batch normalization layer, and in turn the result is passed to the keyword supporting backend. So about the experimental framework, we use the Google Speech Commands dataset for keyword supporting experiments. And this dataset is comprised of more than 100,000 1-second long speech files, and each file comprises one word among 35 possible candidate words. As I said before, as a keyword supporting backend, we use a deep residual neural network, which is trained to spot the 10 keywords yes, no, up, down, left, right, on, off, stop, and go. And utterances with the remaining 25 words of a Google Speech Commands data set, the so-called non-keywords, is to define the filler class. So this involves that the keyword supporting backend has to solve an 11-class classification problem. In addition, the number of Filterbank channels considered in this work is 40. The backend and front-end are trained using categorical cross-entropy as the loss function and Adam as the optimizer, and we employ accuracy as a keyword supporting performance metric. And accuracy can be defined as the ratio of a number of correct predictions over the total number of them. And finally, to draw meaningful conclusions, accuracy results are provided along with 95% confidence intervals calculated from outputs of 10 different backend realizations, trained with different random parameter initialization. So on this slide, we can see the results that we obtained for our Filterbank matrix learning scheme. First of all, it's worth noticing that W, the Filterbank matrix, is initialized by a MEL Filterbank. In this respect, we also tried with with other initializations, but the results or the conclusions we drew were more or less the same. So here in this table, we can see a comparison between using standard log MEL features. So the MEL Filterbank is not trained at all, it's fixed. And we compare this against several different combinations in which we either train the Filterbank matrix from scratch, or we fine-tune the MEL Filterbank after a certain number of epochs. According to this table, we can see that there are no statistically significant differences in terms of accuracy among the different methods tested. Here, similarly, we can see our results for our gamma chip Filterbank learning approach. And in this case, we considered two different types of initialization for the center frequencies F sub k and the equivalent rectangular bandwidths. So now those can be initialized from a linear scale or a MEL scale. And what we can see, which is evident from these graphs, is that depending on the initialization, we end up estimating different values for the learnable parameters. So, for instance, we can take a look at what happens for the length center frequencies. We can see two different trends depending on the initialization as a linear scale or a MEL scale. And despite these differences in terms of length parameters, what we can see in terms of accuracy is that, again, there are no statistically significant differences among the different methods tested. And we arrived to the same conclusion. I mean, the same keyword supporting accuracy trends were observed when using lighter backend models. So to some extent, we can say that these results were expected or not surprising. So, for instance, in the context of speech acoustic modeling, some authors in the past achieved to beat logmail features only by fusing learnable front-end features with the logmail features. And even in this case, it's unclear if this improvement is statistically significant. Nevertheless, we tried the fusion approach. So we decided to combine standard logmail features with learnable gamma chip features for which we use a linear scale initialization. Because the linear scale based initialization may help provide useful complementary information. Nevertheless, again, as we can see, there are no statistically significant differences in terms of accuracy between fusion and the stand-alone, so to speak, approaches. So we might conclude that the learned gamma filter bank conveys no additional information for keyword spotting, and in addition, actually, other fusion combinations that we tried led to the same conclusion. So at this point, a pattern question emerges. Is the filter bank and in general the speech feature design actually a crucial part of modern keyword spotting systems? So to study this question, we conducted keyword spotting experiments using logmail features where we systematically removed filters from the filter bank in order to limit the amount of information available for keyword classification. So filter bank channel removal was carried out around channel 23, the center frequency of which is around 2000 Hz. Since the frequency band contributing the most to human intelligibility is centered near 2000 Hz. So as we can say from this figure, performance is negligibly affected even when removing the channels in the range 20 to 26, spanning approximately this frequency range. So this result supports the hypothesis that keyword spotting systems are fed with a great amount of redundant information, and this should give clues on why performance of learned filter banks and handcrafted speech features is comparable. So to conclude, we have explored two different filter bank learning approaches for keyword spotting. And in general, there are no statistically significant differences in terms of keyword spotting accuracy between using a learned filter bank and handcrafted speech features. And actually, so we can state that handcrafted speech features are still a good choice when employing modern keyword spotting backends. And as we've just said before, the above could be a symptom of information redundancy, and this might involve new possibilities in the field of small footprint keyword spotting regarding the design of much more compact speech features. And that's all. Thank you very much for your attention.